We were discussing infinitesimal canonical transformations. Okay, so I'll just summarize what we were saying. This is the last part of this thing, okay, of canonical transformations. We talked about infinitesimal canonical transformations as these kinds of transformations, okay, delta qi. This changes, I mean, this varies from the identity transformation only infinitesimally. Okay, that's what we meant by infinitesimal canonical transformations. Okay. And we said that such transformations can be obtained from the generator for identity transformation. Okay, this is the generator for identity transformations. We have checked this, right? Plus infinitesimal. This epsilon is an infinitesimal parameter. Okay, Q, P, and T. And when we said infinitesimal, we said that we can what do you say, neglect orders of higher orders in epsilon, right? You need to retain in all calculations, you need to retain only terms up to order epsilon raised to 1. Okay. All right. And correspondingly, we found that delta Pj, right, under this generator, this can be written as minus epsilon dou G by dou Qj, and delta Qj is equal to epsilon dou G by dou Pj. Okay. Okay. Now, yeah, this G is often referred to as the generator of infinitesimal transformations, although the full generator is actually F2, but this G is usually talked about as generator of infinitesimal transformations. Okay. All right. And then we saw that we talked about the active and the passive views and canonical transformation. Canonical transformation actually can be considered as a transformation that takes a point in phase space, all right, a representative point in phase space from one point to another, all right. So we called it as the active viewpoint, right? Okay. So correspondingly, for any canonical transformation, you can have a curve in phase space, all right. A simple example is the time translation. Even time translation can be written as a canonical transformation, and you know that the system point or the representative point, right? I think it's called, yeah, that point in phase space representing our system, it traces a curve in phase space, all right? And this is true for all canonical transformations. Okay. Now, under such a transformation, we found that we can write du by d alpha is equal to u with g, right? So G is the generator, U is some function of the phase space coordinates Q and P, right? We did this. Now, if U is equal to, we looked at the special cases. If U are Q and P, then we have got dq by d alpha is equal to dou G by dou Pi, and okay, instead of U, we take Q first. And if you take P, you see that dpi by d alpha is equal to P comma G. Okay, and that's equal to okay, dq by d alpha can be written as q with g, am I right? Yeah, qi with g, and we know that qi with g is usually written as dou g by, you know, we know this result, right? That's dou g by dou pi. Okay, and p with g is written as minus dou g by dou qi. You can check the Poisson bracket. Okay, we have enlisted this in the properties of Poisson bracket. These things we saw yesterday. Now, these look exactly like the Hamiltonian evolution, right? See, if the parameter is time, okay, and g in place of g you have the Hamiltonian, right? In place of g you have the Hamiltonian. Then you see that these are just the Hamilton's equations of motion, right? You see that dqi by dt if alpha is t. Okay, so this is qi with h, and we know that this is yeah, dou h by dou pi. This is just the equation qi dot equal to dou h by dou pi. right? Also, you see that dpi by dt is equal to pi with h. Okay, this is equal to minus dou h by dou qi. This is just the Hamilton's equations of motion. So we can find Hamilton's equation of motion as a case of canonical transformations. All right. And this corresponds to, as we explained so many times, the evolution or the trajectory of the system point in phase space. So any canonical transformation, okay, whether it's G or whether it's H or P or Q, any canonical transformation can be seen as if the trajectory. Any canonical transformation can be considered as taking the system point, representative point, from one point in phase space to another, and correspondingly you will have a trajectory. Okay, it could be a rotation in phase space, it could be a translation in space, it could be a translation in momentum space. Okay, all corresponding to all this, you get a different configuration. Okay, and then that corresponds to a trajectory in the phase space. Okay. All right. So we are generalizing things. Things look simpler in this formalism. Now, any finite transformation can be written as a series of infinitesimal canonical transformation, right? So we are talking about infinitesimal canonical transformation. If you take a large number of small transformations like that, you get a finite transformation. Am I right? If you take a large number, okay, where the number tends to infinity of infinitesimal canonical transformations, you get a finite transformation. So you can build up a canonical transformation from infinitesimal canonical transformation. You can build up the time evolution from infinitesimal canonical transformation generated by the Hamiltonian. Okay, these are the things we discussed in the last class. All right. Now, yeah. So now let's look at the Noether theorem. Noether theorem is an important thing. It is given in your syllabus. Okay, in the descriptive, in the part, in the what do you say? See part C also, right? So let's also look at Noether theorem. There's a very simple way in which Noether theorem is presented using the formalism of infinitesimal canonical transformations. So we have already seen Noether theorem. In the Lagrangian formulation, we saw that the case of cyclic coordinates is a special case of Noether theorem, whereby if there is a symmetry, there is a corresponding conserved quantity. All right. So if the Lagrangian or the Hamiltonian is cyclic in some coordinates, okay, we know that changing that coordinate does not change the Hamiltonian or the Lagrangian. For example, if Qi, okay, or X, let's say X does not appear in your Lagrangian or Hamiltonian position. Okay, so changing X will not change your Hamiltonian or Lagrangian. So we call it as a symmetry, right? We call if X does not appear, if X is position, for example, right? If X does not appear in your Lagrangian, then changing the position will not change the Lagrangian, right? So if you do something and it does not change the Lagrangian or the Hamiltonian, we say that this is symmetry transformation, right? You do something to it, we immediately identify symmetry transformation, and we saw that this means that d by dt of dou L by dou x dot equal to 0, or dou L by dou x dot is a constant. Okay, so whenever there is a symmetry, there is a corresponding conserved quantity in classical mechanics. In quantum mechanics, it's a bit more involved, but we can say that whenever there is a conserved quantity, there is a corresponding symmetry. The converse may not be true in quantum mechanics. Okay, this was a special case of Noether theorem. So we need a connection between symmetry and conserved quantities. We also saw the general case, okay, where we could consider any symmetry transformation and find the corresponding conserved quantity. We have done problems. Okay, so let's see how it comes about here. Okay, now let's talk about the change in the Hamiltonian. Okay, under some canonical transformation. Right? So we can call it as dou h by dou qi delta qi plus dou h by dou pi delta pi. Okay, so we are making an infinitesimal transformation. How does the Hamiltonian change? Okay, so we take the simplest case where the Hamiltonian does not explicitly depend on time. Okay, so this summation over I is implied. We are using Einstein's summation convention. Right. So whenever this repeated index comes and we don't specify anything, we don't say anything, then you assume that there is a summation. Okay. Now, if there is no summation, we will specify it. If there is no summation, we will specify it. If not, it's always summation. Right? Now this can be written as, because delta Qi in terms of the generator of infinitesimal canonical transformation, we can write this as alpha, or let's say epsilon dou H by dou Qi. What was delta Qi? That was equal to dou G by dou Pi. Okay, minus, okay, there's an epsilon there also, I took it outside. This is dou H by dou Pi, and we have got here delta Pi is equal to minus dou G by dou Qi. Right, if you remember the first things that we wrote. Okay, that minus comes here. Now this is nothing but the Poisson bracket H with G. This is nothing but the Poisson bracket H with G. Okay. So this, what is this? We can call this as delta H. What is this delta H? This is the transformation of the Hamiltonian, or the change in Hamiltonian. We are talking about the transformation of the Hamiltonian. Transformation of the Hamiltonian under some infinitesimal canonical transformation. We call it as ICT. Okay, generated by G. Okay, this is fine. I hope this is clear. All right, delta H, you can call it as the transformation of the Hamiltonian, or it's the change in the Hamiltonian when you make an infinitesimal canonical transformation generated by G. Okay, G, as we said, is often called as the generator of infinitesimal canonical transformations. Okay. All right. Now, what if delta H is equal to 0? What if delta H is equal to 0? Right? So we have seen this often, right? Whenever there's, for example, the time translation, we said that du by dt can be written as u with h. Okay. There may be a parameter here dt. Oh, sorry, dt, I got it here. Right. Similarly, whenever you want to make some transformation, if it's time translation, you just put the generator here. That's a Hamiltonian. Okay. And if it is some other transformation, you put the corresponding generator in this position. Okay. Now, what do you mean by delta H equal to 0? If delta H is equal to 0, we say that the Hamiltonian has not changed under the transformation generated by G. Okay. If delta H is equal to 0, that means that the Hamiltonian has not changed under the infinitesimal canonical transformation, which means that if delta H equal to 0, then this transformation is a symmetry transformation. Right? The Hamiltonian describes the system. So if you do something to a system and the Hamiltonian does not change, then we say that whatever we did is a symmetry transformation. Okay. So this means that if delta H equal to 0, we can call that G is a symmetry. Okay. So we have identified a nice way to find the symmetry of the system. Okay. How do you find the symmetry of a system? All right. If the how do you find whether a particular transformation, how do you find if a particular transformation is symmetry transformation? Okay, you find the generator of that transformation, find the generator. Okay, and if that generator, the commutator with Hamiltonian is equal to 0, then we say that this transformation is a symmetry transformation. Okay, that's the result we got here. Okay, the result we got here, I'm explaining again. Okay, if delta H equal to 0, then we say that whatever transformation that is generated by G, okay, that's a symmetry transformation. All right. Okay. Okay. So under symmetry transformation, this means that delta H equal to 0, then it should be true that H with G is equal to 0. Right? H with G also is equal to 0. Okay. All right. Now, what is H with G? We already know that G with H is equal to dg by dt. Okay, where we are again taking the case where G does not explicitly depend on time. All right. If G depends explicitly on time, you will have a dou G by dou T also, but that complicates the discussion. So let's just get the idea here. Okay. So if H with G equal to 0, this means that minus, okay, this is G with H is dg by dt. Let's also write this epsilon. Okay, or we don't need this epsilon. Okay, or minus dg by dt is equal to 0. Okay, this means that G is a conserved quantity. G is a conserved quantity. Right? So we are seeing the Noether theorem right here. Okay? From the canonical transformation things, we are seeing the Noether theorem directly from this. Okay, what does the Noether theorem say? Whenever there is a symmetry, there is a corresponding conserved quantity, or whenever there is a conserved quantity, there is a corresponding symmetry. Right? So how do you know if whether a quantity is conserved? That's another way to look at it. Okay, you can look it in the reverse order. How do we know whether a particular quantity is conserved? Okay, assume that we are talking about quantities which do not explicitly depend on time. All right, so they are asking whether the quantity, let's say some quantity u is conserved. Right? How do we know whether u is conserved? You just take the Poisson bracket with h, and if it is equal to 0, we say that u is a conserved quantity. All right, but this also means that h with u is equal to 0. Right? This means that there's a transformation generated by u. There's a transformation generated by u which leaves the Hamiltonian invariant. All right. So if there is a conserved quantity, the conserved quantity actually generates a transformation, okay, which leaves the Hamiltonian invariant. Or the converse way of saying it is that conserved quantities generate symmetry transformations. All right. Conserved quantities generate symmetry transformations. So more generally, whenever there's a conserved quantity associated, there is a symmetry of the system. Or whenever there is a symmetry of the system, where delta H equals 0, there is a corresponding conserved quantity. Okay, so that's a very elegant way of describing Noether theorem. Right, it's very obvious here. It's very clear here. Okay, so we can say that if G is a symmetry, then G is conserved. Okay, G is a symmetry, then G is conserved. Right. In quantum mechanics also, we can have the same result using commutator brackets. Okay. Over there, there will be conserved quantities only for those symmetries generated by Hermitian operators. If you remember in quantum mechanics, right? These generators are operators. Okay. And you can see that if a particular transformation is generated by a Hermitian operator, a symmetry transformation is generated by a Hermitian operator, then there is a measurable conserved quantity, etc. That's in quantum mechanics. Okay, so this also is a very good formalism because it shows the mathematical similarity with quantum mechanics. All right, this way of describing things, you can just go from Poisson bracket to commutator. All right, and then you'll get quantum mechanics. Okay, so the mathematical structure is very similar, even though people did not really know about quantum mechanics at the time. Okay, so this is the place, this infinitesimal canonical transformation. So canonical transformation generally, or the Poisson bracket formalism generally, is the point where there's a strong mathematical similarity between classical physics and quantum physics. Okay. So I'll just write it down here. Okay. What we have seen is the Noether theorem again. I'll just write it down here. The change in the Hamiltonian, okay, under an infinitesimal canonical transformation is the change in the value of h as the system point. We are talking about active, okay, system point moves from one phase space point to another. Okay, so this transformation that takes the system from one phase space point to another could be a rotation, it could be a space translation, it could be a time translation, it could be what do you say? Yeah, it could be anything. It could be a rotation, it could be a translation in momentum alone. Okay, it could be anything. Okay, but if the Hamiltonian does not change under all these conceivable transformation that you think about, then the transformation is a symmetry, and correspondingly you have a conserved quantity. Generator of that transformation is a conserved quantity. Okay, all right. So it's a generator that is conserved. Okay, and if h does not change, this is a symmetry. This is a symmetry. Okay. right? And correspondingly, the generator of the ICT is conserved. Okay, conserved quantity. All right. Now we talked about the case where G does not explicitly depend on time. If G explicitly depends on time, the treatment is a bit more general. You can check Goldstein if you are interested. All right, but this result is enough for us to understand the Noether theorem. Okay. Now, if it is changing, if G depends explicitly on time, then we would have change in Hamiltonian would be written like this. Okay, as you expect, there would be an extra dou G by dou T term. All right. Again, we can write if so yeah. All right. Let's yeah, alpha. Okay. So again, you can write delta H or dou H is equal to minus dg by dt. Okay. This is always true. This is always true. Okay. This is always true because now this is the total derivative. Right? If G does not explicitly depend on time, we don't have that term. That's all. Okay, but that's just a detail. You can look into Goldstein if you are interested. Okay. All right. So that is Noether theorem all over again. Okay. Now they can ask you may be able to solve some simple problem if you know the proper generators and corresponding conserved quantities. All right, or you can find the Poisson bracket using the generator and check whether it's a symmetry or not. All right, these things can be done very easily by using the Poisson bracket relations. All right, let's talk a little bit about generators now. Okay, we said that G is generator usually. All right. Now I want to go into the details. It's easy to remember. We know that momentum is the generator of space translations. Okay, momentum is a generator of space translation. Okay, this is not very true. All right, so momentum generates, let's say, delta Q, a change in Q only. Change in coordinates only. Now, this is obvious, right? Because Qi with Pj, okay? If you have an epsilon there, that's a parameter by which you are changing, okay? This is equal to epsilon delta ij, okay? Delta ij, okay? Now, we know that Qi with Pj, right? In this case, this is delta Qi, right? So, delta Qi is equal to epsilon delta ij, which means that if it is P1 here, it changes only Q1. If it's P1 here, it changes only Q1 by an amount epsilon. Okay, so basically this is this. It takes Q to Q plus or Qi to Qi plus epsilon. Okay, if the generator is Pi, right, or we can say Qi to Qi plus epsilon delta ij, right? Because if P is the generator, momentum is the generator, it generates a transformation, a change only in the corresponding coordinates. Okay, coordinate, right? Now, so we can say that momentum is the generator of translation in coordinates or change in coordinates. Okay. Similarly, you can see that L is a generator of rotations. L is the angular momentum. We have already seen this. Okay, L is the generator of rotations. Okay, so if you need a rotation about a specific axis, if it is about z axis, if you need to generate a rotation about z axis, then it's Lz. We can say Lz, the z component of angular momentum. Rotation about z axis. Okay. Now, generally, we can say if you need a rotation about some unit vector n cap, some direction given by n cap, then we can say that L dot n cap is the generator. Okay, what is n cap? It's some arbitrary direction in space. Okay, if you need to generate a rotation about some arbitrary direction in space, you just take the angular momentum and project it along that direction. Okay, L dot n cap, that gives you the component of L vector, the component of L vector in the direction n cap. Okay, that would generate the rotation about the n cap direction. Okay, all right. And there is some important result here. We have already discussed this. Okay. Fi for any system vector. System vector is a vector that depends only on Q and P. Okay. Fi with Lj is equal to epsilon ijk sk. All right. This is actually a rotated thing. We know that. And this is a system vector. This Fi is a system vector. Okay. And we have seen special cases of this in the angular momentum Poisson brackets. Okay. If this is, for example, Li with Lj. Okay. Li is also a vector, but it's getting rotated. So it is epsilon ijk Lk, like that. Okay. Or generally, we can have this result. You may, this results, having seen this result is good. You can. We also know that epsilon ijk corresponds to a cross product, right? So we also have this result. If you have some vector f vector, comma l vector dot n vector. Okay, this can be written as n cap cross f vector. So if you take one component of it, you see that you'll get that. Okay. Generally, f vector, comma l dot n cap, okay, unit vector. That's equal to n cap cross f vector. Okay. So these are all related to the rotation, okay, to the fact that angular momentum are the generators of rotation. Okay, angular momentum are the generators of rotation. I hope these things are clear. Okay, and we can look at Q. All right, Q, it's easy to see. What about Q? Okay, if you take the coordinates and take Qj, this is always 0. So if we take position, or if we take coordinates as the generator, okay, if you take the coordinates as the generator, it does not change the coordinates. It does not change the coordinates. All right. What about momentum? Pi with Qj. Okay, you see that this is equal to minus delta Ij. All right. So it changes the momentum. Right? If you take coordinates as the generator, it changes only the corresponding momentum. Right? Because they are conjugate to each other. Changes only the corresponding momentum. So if you have an epsilon, you'll have an epsilon there. So if you take a particular Q, there is a corresponding conjugate momentum P, and it changes that momentum by a small factor, by a small change epsilon. Right? So that's delta Pi is equal to minus epsilon delta Ij. Okay, it's generated by the change in momentum alone is generated by generator Q coordinates. Right? And finally, H is the generator of time translations. Time translations. Okay, and if H does not explicitly depend on time, we know that delta H. Okay, how do we know whether the energy is conserved? If energy is conserved, the transformation generated by H has to be a symmetry, which means that delta H has to be 0, or H with H is equal to 0. This is true, right? H with H is equal to 0. We have taken the case where the Hamiltonian does not explicitly depend on time, etc. So the conservation of energy has a very simple form in this way. Right? So it's conservation of energy. And do you see that there's a deep connection between specific transformations and certain generators? All right, there's a connection between energy and time. There's a connection between position and momentum, momentum and position, rotation and angular momentum, etc. Okay. Now, just in order to complete our discussion, you can be asked certain questions, in multiple choice questions. So it's important to have some information regarding this. Right? They can ask like, which among the following is true, and they may give you a few statements, and you have to look at them and know whether this is conceptually correct. Okay. So there's something that we left out. We need to talk about canonical invariance. Canonical invariance. Okay. Which means that we are talking about canonical transformations. There are certain quantities pertaining to the system which do not change under a canonical transformation. Okay, which do not change under a canonical transformation. The first example, we have already seen that the Poisson brackets. We won't do any proof here. Okay, the Poisson brackets are invariant under canonical transformation. We said that U, V, whether it's with respect to the old or new, it's the same. All right. Poisson brackets are canonical invariants. All right. There's also another thing called Lagrange brackets. It's rarely used anywhere, but it's a construction that also leaves that's also Lagrange bracket is also a construction that is invariant under a canonical transformation. Lagrange brackets. Okay. So we'll use the curly brackets for this. Its definition goes like that. So it looks just this is dou q by dou u, dou pi by dou v. We know this definition, right? This is equal to dou u by dou qi, dou v by dou pi minus dou u by dou qi, dou v by. Okay, this is the Poisson bracket and this is the Lagrange bracket. You see that here you have a dou u by dou qi. In this case of Lagrange bracket, you have dou qi by dou u. Okay, it's easy to remember. Minus dou pi by dou u, dou qi by dou v. All right. Now, what's important of this? We are not going to solve any problems using this. We are not even going to prove that this is invariant. I'm just giving it to you that this is invariant under canonical transformations. And if they ask something about this, all right, which among the following statements is true, that this is an invariant or it changes under canonical transformation, you know how to pick the correct answer. Okay. There's also the magnitude. Another important canonical invariant is the magnitude of volume element. Magnitude of volume element in phase space. Okay. So what do you mean by a volume element? Right? So suppose we represent all the coordinates by eta. Eta means q1, q2 up to qn and p1, p2 up to pn. Okay, just give it a name. These are the old coordinates and the new coordinates will represent by zeta. q1, q2, qn, p1, p2, pn. Okay. These are the old coordinates and the zeta correspond to the new coordinates. So we are just giving them a collective name, eta and zeta. Right? Now the magnitude of the volume element remains the same, means that d eta, okay, is equal to, this is the volume element, right? D eta. This is simply dq1, dq2, dqn, and then dp1, dp2, dpn. This is what we mean by d eta. All right, this is the volume element in the old phase space coordinate, and in the new phase space coordinates, this is equal to d zeta is equal to dq1, dq2 up to dqn, d capital P1, d capital P2. Okay. Now this construction, this is the volume element. All right, we know that in a three-dimensional space, the volume element is dx, dy, dz. Okay, if you change into another coordinates, the corresponding volume element would be dy, dx, dy, dz. Okay, here we are talking about 2n dimensions, so there are 2n coordinates instead of just 3 here. Okay, that's the volume element, and this is invariant. Okay, this is invariant. All right. Now, how do we know whether this is invariant? So okay, we use the fact that, okay, it's again a statement that you need to keep in your mind. Okay, under coordinate transformations, okay, here coordinates could mean any general kind of space. Okay, it could be even phase space. Coordinate transformation, the size of volume element, volume elements are related by the absolute value of Jacobian determinant. Okay, do you know what a Jacobian determinant is? You might have used it in many places. All right. So when we go from, for example, x, y, z to capital X, capital Y, capital Z, dx, dy, dz is not directly equal to dx, dy, dz. Okay, this is true only if the Jacobian is 1. Okay, there's actually something else sitting here that's known as the absolute value of the determinant of the Jacobian matrix. Right? What's the Jacobian matrix in this case? In this case, the Jacobian matrix is this: dou x by dou x, dou x by dou y, dou y by dou x, dou y by dou y, something like that. Okay, there's I'll just take 2 dimensions, so I'll have to write one more step, right? Okay, that's correct. Okay, this is known as the Jacobian determinant. In our case, let's look at a 2-dimensional case, all right? A 2-dimensional phase space, which means we are talking about 1 dimensions. So the phase space has 2 dimensions, right? So let's take an example, a 2-dimensional phase space. Okay, we have got eta I are q comma p. There are just 2 dimensions, 1 coordinate and 1 momentum, and the new coordinates zeta I are q comma capital P. Right? What's the Jacobian? What's the Jacobian? We can say that dq. All right, dq dp. This is the volume element in the new phase space. All right, this is the volume element in the new phase space. Okay, this is equal to dq dp. Okay, so determinant, more absolute value of the determinant. What is this determinant? By construction that we have constructed here, it is this. It is dou q by dou q and dou q by dou p. Okay, dou p by dou q and dou p by dou p. This is known as the this is known as the Jacobian matrix. Okay, we are taking the determinant of Jacobian matrix. We also need to take the absolute value. Okay, we call this as M. And in this case, it's very simple. Okay, what's the determinant of this? It is dou q by dou q, dou p by dou p minus dou q by dou p by dou q. All right, we need to take the absolute value of this and then dq dp. Right, and here we know simply that this is simply the Poisson bracket of q with p under the new coordinates, and we know that this is equal to 1. Am I right? So this is equal to dq dp. Right? So for 2-dimensional case, for 2-dimensional phase space, we have actually proven using the invariance of Poisson brackets. Right? Using the invariance of Poisson brackets, we have proven that the volume element remains the same. Volume element does not change. Right? Now, if a volume element does not change, then if you take a some volume integral dq dp, some volume, then this also will be equal to, or generally dq1 dqn and dpn dp1 to dpn. Right? If you take some volume, find a small volume, this is an infinitesimal volume. If you integrate, you get this is also invariant. This is also invariant under canonical transformations. Okay, so volumes are invariant under canonical phase space. Volumes are invariant under canonical transformations. Right? Now, in the case of 2 dimensions, this Jacobian determinant becomes just the Poisson bracket. Okay, we already know that Poisson brackets are invariant, or that can be taken as a definition. So you can also do it in this way. Okay. Right, so what I need you to remember is this. The Poisson brackets are invariant. The volume elements are invariant. Volumes in phase space. If you take a small volume in phase space, just by transforming just by making a canonical transformation, you cannot change the volume. Okay. All right. So generally, you can say that d eta equal to d zeta. Eta is a set of any coordinates. Okay. So the volume of any, we also saw that this automatically implies that the volume of any arbitrary region in phase space is also invariant. Okay, so the volume will remain the same. Now this statement, it has been asked in a previous question paper, in which among the following is true. Okay, and they have given an option, the volume in phase space remains the same. Okay, under time evolution, they have said under time evolution, but we know that the time evolution can be written as a succession of canonical transformations. Right, so this means that the volume element does not change under a time translation. Right, under time evolution, under Hamiltonian time evolution, the volume in phase space of an arbitrary region does not change. Okay, I hope that's clear. This was asked for a question, right? This I don't remember, but it was asked. It was one of the statements in choose the correct answer, or choose which among the following is true, right? This is under canonical transformation. Okay, if it is invariant under canonical transformation, this means that it is also invariant under time translations. So right, this was the question asked under Hamiltonian evolution. Okay, so this is something you need to remember. Also invariant. All right. And also in view of such questions, we need to discuss this theorem known as Liouville theorem. You have to check the spelling. Okay. Liouville theorem, right? Now, this Liouville theorem you might have already seen in statistical mechanics. Okay, but I'll just give you the canonical transformation way of proving it. We don't do the exact mathematics and all that. I'll just give you the statement. Okay, and yeah, that will do it. Now we know that the whole system, all right, whether it's a gas of 10 raised to 23 molecules, etc. Okay, the whole system can be represented by one point in the phase space. Okay, where the phase space is 2n dimensional. Okay, so corresponding to the whole system, a box of gas or a cylinder of gas, okay, the position and momentum of all the coordinates, sorry, all the atoms of all the gas molecules is represented by one point in phase space. Okay, this is known as microstate of the system. Microstate. What do you mean by microstate? You take the system, whether it's a gas or a liquid, all right, and you write down all the coordinates. Okay, all the coordinates and the momenta or the complete state. Microstate is just a specification of the complete state, exact state. Specification of exact state of the system. Okay, this is known as the microstate, right? And that corresponds to one point in the corresponding 2n dimensional phase space. Okay. Now, if you take a system with large number of atoms, let's say of the order of Avogadro number, right? If there are a large number of molecules, then you really cannot keep track of all the position and moment of each particle. We don't do that. In statistical mechanics, we know that we only study what is the total behavior and average it. Okay, and we cannot know. It's impossible to know the microstate, the exact microstate of the system when we are talking about 10 raised to 23. And even if you can know it, it takes too much calculation and space, etc. It's not possible. If you take a gas, you simply cannot. Or it's true that even if you take a gas, each molecule will go according to the equations of motion, but you cannot track each molecule. Right? You cannot track the exact microstate. So what we do is that we are not sure about the exact microstate. We talk about a macrostate, it's a different specification of the system, but with much less information. Right? If you take the microstate, you have the complete information about the system. So we talk about a macrostate, which has much less information. All right, but then there can be a number of microstates corresponding to the macrostate. Okay? So we talk about ensembles. In statistical mechanics, we talk about ensembles. Okay? Ensemble means that you don't take the exact information. What you do is that you just look at the system as a whole and you define some microscopic things like the total energy, the total number, the total volume of the system. All right. And but there is a large number of arrangement or large number of microstates which would give rise to the same macrostate. All right. So we talk about ensembles. So instead of pinpointing the system in the phase space, okay, if you pinpoint the system in the phase space, you got the exact state of the system, QIPI, right? But it's not practical. So what you say is that we talk about an ensemble of systems. Talk about an ensemble of systems. This ensemble corresponds to a swarm of representative points. Swarm of representative points. It's a collection of representative points. Okay. Now each point here corresponds to a completely different configuration of the completely different microstate of the system. Okay. This is the whole gas, all right, represented by one point in the phase space. Okay. So each point corresponds to a different microstate. So when you look at this system, what you see is the evolution, and each of these phase space points, okay, each of this microstate evolves according to the Hamiltonian equations, right? And the initial conditions completely determines the future evolution, right? So what you see is actually a flow of representative points in phase space. It's similar to a fluid flow. It's in many ways it's similar to a fluid flow, right? So this is the case where this is the kind of thing that we use in statistical mechanics, all right? So ensembles are actually copies of the same system, right? And each copy, in principle, can have a different microstate, a different configuration, different state. Okay. So the macrostate and microstate, these are just two different specifications of the same state. Okay. In microstate, you don't have the exact information. It's a specification of the same state. Okay. If you have a box of molecules, right? If you have a cylinder of gas, okay. Macrostate means that you choose to, for example, you choose to only talk about the energy, the total number, and the volume. Okay. Microstate, and here we don't have so much information. So much information is thrown away, and then we talk about entropy, etc. Okay. And microstate means that you give the complete specification of the system. This is known as a microstate. Okay. All right. And when you take microstate, there can be a large number of microstates corresponding to the same macrostate. Okay. So different configuration can give you the same appearance. Okay. And the number of such different configurations corresponding to macrostate is associated with entropy. You know all these things, right? But we are interested in the flow of these representative points in phase space. Okay. All right. So what I wanted to say is that we talk about ensemble, and ensemble can be seen as a swarm of representative points or a collection of representative points. Okay, and each representative point corresponding to a different microstate. Right, you might have seen this. Now, what does Liouville theorem say? Liouville theorem, I'll give you a statement. This also can be asked in multiple choice questions. Right, Liouville theorem says that this is a very important theorem. It has to do with reversibility. It has to do with conservation of information. It's very important. Okay, so the density of systems in the neighborhood of some given system in phase space, remains constant in time. Remains constant in time. Okay. So density of systems in the neighborhood of some given system in phase space remains constant in time, which means that if you take a system and you take a neighborhood of it, all right, so there is a volume. There are so many representative points enclosed in this volume. There are so many representative points enclosed in this volume. Okay. Now, the density, okay, the number of representative points divided by the volume enclosing, that's the density of representative points, remains constant. It cannot change. Okay. Now it's easy to argue this using canonical transformations. It's easy to argue this using canonical transformations. Okay. So what do you mean by density? Density means it is basically, let's say, the total, let's say dn by dv. Okay, dn by, I think you should write as dd. Okay, that's dn by dv. So dv is a small volume enclosing dn number of representative points. All right. Now we can easily argue that this n remains the same. If you take a volume, the n remains the same. How? We can easily argue this. Suppose there are, this is the volume, all right? And when you take a volume, there is a surface. This is a 2n dimensional phase space. So you have got a 2n minus 1 dimensional surface. Okay, enclosing the volume. Am I right? Yes? Yeah. So if you take a sphere, you know that there is the sphere is 3-dimensional, but there's a 2-dimensional surface enclosing the sphere. In the same way here. Okay. Now we are saying that if you take any volume like that, the number of representative points inside this volume remains the same. Okay. How do you argue this? It's easy to argue. Imagine this representative point is getting out. Okay. Imagine that this representative point is getting out. But when it gets out, it has to go through the surface. Am I right? It has to go through the surface. All right. But if it reaches the surface, okay, it will occupy the same state as one of the points in the surface. Am I right? If it reaches the surface, the surface is also defined by so many, what do you say, representative points, right? The surface is defined by, it's a surface in phase space, and each point on the surface is a possible representative. It's a possible point in phase space. Okay. Now, if it reaches the surface and it matches with one of the states on the surface, okay, and then the evolution from here is completely determined by Hamilton's equation, right? So the surface evolves according to deterministically according to Hamilton's equations, and we know that once the initial state is given, the future evolution is completely specified. All right. So if it reaches the surface, then it evolves with the surface. Okay, and so there cannot be particles or the representative points escaping the volume. I hope this is clear. Right? So the surface as such, any arbitrary surface you define, the points inside cannot get out. So because if it reaches the surface, then it evolves with the surface. It cannot cross the surface. Okay, that's just the deterministic evolution of Hamilton's. It's exactly saying that, you know, we said that the trajectories cannot cross. If the trajectories cannot cross, right? So if the representative point gets out here, this means that the let's say, for example, the surface is evolving in this way and the point got out. So corresponding to this point, you have got two different trajectories. Am I right? Corresponding to this point, you will get two different trajectories, and this is not allowed. Okay. So the number inside the volume remains the same by this argument. What about the volume? The volume also must remain the same, because we said that it's a invariant under canonical transformations, and time translation can be written as a canonical transformation. So volume also remains the same. Volume also remains the same under time translation, because time translation is a canonical transformation and volume elements are invariant under canonical transformations. This means that d by dt, this means that d also should remain the same under time translation, all right, or time evolution of system. This means that d by dt is equal to 0, or in other words, we can write this as d with h plus dou d by dou t. If it has an explicit dependence on time, this is equal to 0. This is known as the Liouville theorem. Or we can write it as d with h is equal to minus dou d by dou t. Okay. All right. This is known as the Liouville theorem. And what does this mean? Suppose you have got a phase space like this and some volume like that. Okay. Okay. So, and later you may have some different distorted volume, but this volumes must be the same. Okay. This is Q of T1, P of T1. This is Q of T2, P of T2, but at a later time. It may have a distorted volume in phase space. It can completely distort. beyond recognition, right? But the volume will remain the same, right? Also, the density of representative points will remain the same. That's what Liouville theorem says. Okay, I hope that's clear. Okay. Now, you will see in statistical mechanics that statistical equilibrium means dou d by dou t is equal to 0, right? So this is the condition for statistical equilibrium. All right. This means that the number of systems in a given state, right? Number of systems in a given state, it remains the same. If there's a particular state, the number of systems in that state will remain the same. That's known as statistical equilibrium. So that's Liouville theorem. And that's enough for us. This treatment is enough. And there may be some multiple choice questions of the kind I described. Okay, it's good to have this in mind, this Liouville theorem, and the fact that the volume remains the same, the density of representative points remains the same. Okay, and all these are consequences of the Hamiltonian evolution of the system. Okay, all right. If you have any questions, you can ask now. With that, we'll conclude canonical transformations. All right, there's a small section in theoretical formulation known as the Hamilton-Jacobi theory. In the next class, we'll continue with that next week. Okay, we'll continue with Hamilton-Jacobi theory. Okay. All right. If you have any doubts, you can ask now.